Hello, everyone, and welcome once again to today's webinar. This is one of a series of Fronius webinars where we discuss Fronius products and solutions. And today we shall be discussing PV-Genset integration with Fronius Inverters and third-party controllers. And to do this with me today is Byron Kutzer. Byron Kutzer is the Technical Sales Advisor for the Southern Africa region, of course, for Fronius International. He is based in Johannesburg, South Africa. And of course, myself, Sipra Nkolo, I'm the Technical Sales Advisor for the Western Africa region, based in Lagos, Nigeria. So together, we will be presenting today's webinar, hoping you'll enjoy it. So let's go through what we have for you today in the agenda. So we shall be having a brief overview of the solution, why PV-Genset, we'll be answering that question, and then have a look at the definition of the solution, how it is set up, and then with the introduction of the Genset system controller. Byron will step in this point to continue with a couple of references, go through operational timeline of the solution, how Fronius supports in terms of the implementation of the solution, give you a brief of the inverters we have for use for this for the implementation of the solution, and then the communication interface between Fronius and of course the third-party controllers. So afterwards, we will be giving you conclusive information afterwards. So without further ado, let's continue. But then before we start, please feel free to ask your questions during the webinar. We will endeavor to answer all your questions during the course of the webinar. In the case where we are not able to do so, probably because of time or insufficient information, we will, of course, get through to you individually with your respective responses. Yeah, so we value your opinion. So please, we would be happy to have your feedback about the content of our webinar. So let's start off by giving us an overview of the PV-Genset solution. And in so doing, I would want to dispel some myths or misconception about gensets and consumption, fuel consumption. So there is, well, for those of us that already know, please you'd have to indulge me for a brief second. There are a good number of people or clients or even system owners or factory owners believe that the rate of consumption of fuel or gas, as you may know it, is constant so long as the genset is powered on. So this is the concept or the belief that these set of people have. So they believe that once the genset is on, then the rate of consumption of fuel is constant, is the same. But this is absolutely wrong. The truth is that the rate of consumption of fuel is directly proportional to the load demand. So meaning that the more the load demand, the more fuel is combusted or consumed. Okay, so and then the more the load demand, it means the more fuel is consumed, just like I mentioned earlier. So what basically causes this is, yeah, of course, just want to use a scenario to explain this. So you might, or all of us would notice that there is a consequential change in pitch, or you might want to call it sound of the genset once a heavy load is applied or a heavy load is turned off. So this is basically the action of the governor, basically the component of the genset that is responsible for controlling the valve through which the fuel passes through into the combustion chamber somewhere here. So basically what happens is if a heavy load is turned on, then the demand for power increases from the load side, obviously. So there has to be an increase in power coming from the genset. This is only possible if there's an increase in the fuel quantity coming into the combustion chamber. So the governor basically pulls the valve open, or makes the valve to come to have more inlet or more incoming fuel into the combustion chamber. So once this happens, this leads to a higher power being generated from the gensets. But of course, we know that the more fuel is consumed, of course, that will generate to lead to a higher power to meet what is requested from the load point. So what this means is that if it is possible to alleviate the fuel consumption, then it will make a whole lot of economic sense. And then the best way to do this so far is by injecting PV into the system. So once PV is injected into the system, it goes a long way to reduce fuel consumption, thereby making it the most economic setup for such installations. So having said so, let's continue to give us reasons. Of course, I've already mentioned one reason why PV-Genset, but then in order to add to them, of course, it provides stability for the entire PV-Genset system. And then this is done through easily integrated means into an existing genset. While it's not only meant for brownfield implementation, that is for an already existing genset system, it is also applicable for greenfields, that is new installations, right? So of course, it goes a long way to save money because of course it lowers your energy prices and then saves you a whole lot on fuel expenses. A good business case for this is that it comes with a high rate or rapid amortization, meaning that once you're able to, although of course the capex is relatively high, but then with a short amortization period, it makes a whole lot of economic sense in terms of making a business case for it. In addition to this, it helps to decouple from overdependency on fossil fuel and consequently or subsequently reducing the carbon footprint. Great. I can see that the questions are coming in, so please keep sending your questions, and of course we will endeavor to answer each and every one of them. Great. So how is this system defined, or basically how is it set up? So we'll start by defining the components of this entire system. So first up here is the inverter, which is the Fronius inverter, obviously. And then, of course, the inverter is responsible for providing PV into the system, or injecting PV into the system. Then we have the genset, which tends to be the primary source of energy for the system. We'll discuss more on that in the subsequent slides. And then we'll have the control mechanism, which I fondly call the brain of the system. Although it looks small, but then it is in terms of mighty, in terms of the function that it performs for the entire system. So this is basically the decision maker. It is the one that makes the decision on how and when to inject PV into the system in the most appropriate manner. And then, of course, we have the load point that must be served with as much energy as it is demanding. Good. So I'm going ahead to give us a single line diagram, and we'll go ahead, a single line diagram of the entire system, how it looks like. And of course, we'll go ahead to define each and every one of them in more detail. Yeah, so this is basically the Fronius inverter. In this case, we're referring to the Tauro, but of course, Byron will give us more details on other inverters, Fronius inverters that can be used to implement this solution. So basically, the inverter converts DC to AC, thereby providing as much PV as possible for the system. Next up is the system controller. Like I mentioned, the brain of the system. So this basically measures all the power flows in the system, enabling it to control the PV power in the most optimal manner. Next up is the genset, which basically is the primary source of energy for the entire system. And of course, it is usually relieved by the injection of PV into the system, which eventually saves fuel. Next, we have the load point, which must be supplied. And then this supply is usually a mix of fossil and solar energy, depending on the scenario. The next up is a very critical component, which is the current sensors. Yeah, so this current sensors communicates with the system controller. So this measures the current, which is usually proportional to the load demand. So this enables the system controller to know exactly what the load demand is. And then with the knowledge of this and with the pre-configurations that have been done, it is now able to make the decision on how and when to inject PV into the system. So just to give you an instance of how this works, let's assume that we have a load point here that is demanding 100 kilowatts. Well, to start off, as a rule of thumb, it is absolutely imperative to ensure that you rate your genset so that it would be able or should be able to supply 100% of the load demand, the peak load demand. This is basically the first rule of thumb in designing a PV genset solution. Ensure that the capacity of the genset is enough to provide for 100% of the peak load demand. So once that is done, then we can now go ahead with the other components in terms of the system design. So let's go back to the example I was talking about. So let's say that the system or the load is demanding 100 kilowatts. So what happens is, assuming that we have a generation of 700 kilowatts from the PV, okay? So what this does is the system controller notices that 100 kilowatts is demanded from the load. And if it sees that the PV can generate or is generating as much as 70, yeah, just to be sure with the mathematics, yeah, 70. So what it does is to pull in the whole 70 kilowatts into the load line, and then throttle the genset down to 30 kilowatts, thereby getting a good mix, 70 from the PV and then 30 from the genset to provide for 100 that is demanded from the load side. So that's just basically how it works. So of course, as you've noticed, this is absolutely dependent on what is being generated from the PV. If this is 60, then it will throttle this one up to 40. If it is 50, this will be 50. Just as long as there's a good combination to provide for the entire load demand, basically. Good. So lastly, in the component definition, we have genset. Yeah, I mean the grid. So it is also possible to have the grid connected in the system. Yeah, because once the grid is available, then there will be absolutely no need to burn any fuel. So, but then in regions that usually don't have sufficient grid, this actually this solution actually comes into play and becomes very, very handy. So going forward, I'd like to mention that this PV genset solution comes in, I would say, two modes of implementation. It could come in the low penetration mode. So for low penetration mode, these are typically defined by the PV injection or the PV penetration. So if you have a PV capacity that is, say, 20% capacity of the genset, then in this case, it is not absolutely necessary to use a genset, a PV genset controller, okay? Because of the low penetration. So it doesn't present any danger at all to the genset, even in the case of low or high irradiation, okay? So, but in a case, but the effect of this is that you're going to have a long ROI period. The return on investment for such implementation is usually very long. So it is usually advised that in order to have a quick or short amortization period, high penetration mode is recommended. But then, once adequately calculated, there are some cases or period where you're going to have an overshoot of PV in the system. So this presents a danger to the genset because it would end up feeding back into the genset, which isn't desired at all. Of course, because it has a debilitating effect on the genset. So in order to forestall this, then that is where the PV genset controller comes into play. So let's now have an overview of how this system can be designed. First off, as mentioned, we need to know the minimum genset loading. So basically, the minimum genset loading falls between 25 to 30%. So for those that don't know, the minimum genset loading point is a point that the loading of the genset must not go below. Okay, so this is usually 25 to 30%. So if you're loading a genset, it mustn't be below 25 to 30% of the genset capacity. Because if this happens, it has a negative effect on the genset. It would lead to wear and tear, development of mist and sludge on the valves and the lights. So this is absolutely not desired. So this information can be found on the nameplate of the gensets. Okay. So now once this is ascertained, you would now have to also ascertain the peak load demand. This can be ascertained gotten from the load profile. So from the load profile, you should be able to get the maximum or peak load demand. So with this power window per se, as in maxima and minima, then you can now be able to estimate the inverter power that will be used for this particular system. Okay, and then given the fact that Fronius Inverters has the capacity to be overdimensioned up to 150 or up to 150 or 120%, with that, you would now be able to know what your maximum PV power for injection into the system would be in kilowatts peak. Okay, so this basically gives us an a general overview of how a PV genset system can be designed. Good. So customer segments or target clients includes, but of course not restricted to these, including factories, tourism, especially in remote areas, mining industry, most especially because most mining industries are located in very remote areas that are hard to reach, and then with insufficient or no grid supply. And then of course, food processing industries. So, but basically, this solution comes into play when we have a scenario where the genset almost runs perpetually, that is, if not perpetually. Yeah, so basically, that's how we roll with the PV genset solutions. I would want to mention that it would come in various fashions. We have the PV Genset Advanced and the PV Genset Professional, which I'll be shedding more light on in the subsequent slides. But I'll just also want to mention here that for all our clients that already have the PV Genset Easy already installed, there's no need to worry. We will, of course, continue to support you with your installations as time goes on. The reason being that the PV Genset Easy solution has been discontinued for now. And yeah, so, but for all those that already have it installed, we continue to provide maximum support. So what is PV Genset Advanced and Professional? So we're just basically going to relate it to brownfields and greenfields. So for brownfield installation, that's where PV Genset Advanced comes into play. Basically integrating PV Genset solution into an already existing genset system. So this usually have you implementing the solution with a PV Genset controller brand that is different from the brand of the genset system. But for the professional solution, in most cases, comes as a greenfield installation. So both the genset, the system controller, usually of the same make or manufacturer. Good. So, but if you look critically, you find that in this, there's a bit of flexibility that has been added to this particular solutions. In both cases, you can see that there is a possibility to include storage. And it is typically applicable for cases or industries where you have specific periods or times when low energy or low power is needed. So a typical example includes, say, a factory that works from Mondays to Fridays. That's during the working days of the week. That's Monday to Fridays, based on the region, per se. So, and we now find that Saturdays and Sundays, the only loads that are connected or supplied are just lighting, perimeter lighting, and then a few socket points. So it wouldn't make sense to have the genset running just because of these small loads. So it makes a lot of sense to have it being supplied by the storage facility over the weekend. And then once Monday comes around, which is the beginning of a new working week, then the gensets can now come into play. So this comes in as a very flexible addition to such PV genset setup. Great. Okay, so this brings me to the end of my part of the presentation. Byron will now be continuing with the rest of the presentation.
So next we'll be covering is the references that we have regarding PV genset integrations. So for starters, we have a reference coming from Lebanon itself, where the specific system size is 144 kilowatt peak. You've got a generator integrated in the system, which is 280 kVA. So the purpose of the system is to do PV genset system integration for vegetable plantation that they have. For this example, we have 6 Fronius Simo 20 kilowatt inverters installed in the system itself. And then obviously we have our 280 kVA generator in the system. So the annual yield is about 216,000 kilowatt hours per year. The CO2 saved per year for the system with the integration of the PV and the genset itself is 114.5 tons that they are saving annually. And the special feature is allowing us a 40 degree of self-sufficiency in the entire system per year. And this system has been commissioned since December 2014 and is still running till today. So this will help with boosting your return on investment or your ROI. So we can see on the PV system, we've got a 0.15 euro cents per kilowatt hour that we are generating, as well as for the generator itself, we have 0.5 cents, euro cents per kilowatt hour. Again, the installed capacity is 114 kilowatt peak. And the annual yield for the PV plant, which is again uncirculated, which is 200,000 kilowatt hours per year. So the total cost of the PV system plant, which is 216,000 euros, for example, and the annual savings with the PV system itself is about 45,000 euros per year. So this allows us to get an ROI-based estimate within 4 to 6 years for the return on investment. And then from the 5th year, or the years subsequent from the 6 years onwards, we can see a saving of 68,500 euros per year in terms of your return on investments. We also have a reference plant in Madagascar. So here we have a system size of roughly 350,000 watts or 350 kilowatt peak. We've got 2 generators in the system. So we've got 2 500 kVA generators in the system. This is for a textile production factory. But here they're using 10 Fronius Eco 25 inverters, and they're also using a control unit of the DIVE 150 hybrid. And their annual yield is about 495,000 watts per year, for example. The special features, it's brownfield and mains with the addition of the PV and the genset into the system itself. The general PV genset design recommendations. So again, the 30% minimum rule that Cyprian was referring to with regards to the genset loading, but unless it is stated differently by the genset manufacturers. So what we have noticed is a few manufacturers have gotten into an idle state with regards to their generators configuration, which allows them to burn up to 5 liters per hour, depending on the model and manufacturer that you're using. So this does vary depending on the generator itself, as well as the manufacturer that you're using. But we always recommend is to always consult with the manufacturer of the generator to then get this exact value that the generator is then comfortable with in its operating mode. Again, the maximum AC inverter power should not exceed 60 to 70% of the generator power. So we can't match it at 100% to both, for example. So what happens is we'll only utilize 60 to 70% of the maximum power for the genset itself. And again, we have our DC to AC ratio to be the maximum. So use different orientations to synchronize with the consumption curve. So obviously making use of east-west orientation on our modules to help maintain that we have that peak PV generation throughout the day whenever the genset is running, for example. So on the PV genset system operation timeline, so here we can see we have our consumption values. So this blue line here, we can see that we are running a consumption load that's automatically switched off, for example. And here we have our PV graph. So here we can see the consumption as well as the genset's operation, and then our PV estimate. So we have here is the PV running and then the PV available. So this is referring to the kilowatt peak that Cyprian was referring to. So this is the estimate of what the PV system could generate in the system itself at that time of day. And also we have our minimal load. So all of a sudden, if we have a sudden loss or disconnection of a load, so obviously the system will need to power down, but if we didn't have a controller in the system, we would then still be producing that power, for example, in the system itself. So with the controller, it allows us to automatically switch down the system itself, which allows for extremely fast reaction from the PV. So then ramp down in conjunction with the load being lost. So we're not pushing any energy back into the genset itself. Again, it's the same principle when the load all of a sudden comes back. So when the load has come back, we can then see that the PV is then switched back to 60 or 70% of the loads itself to then help stabilize the load injection that we need for the system itself. So next is the power range recommendations. So again, this is for PV system advanced. So anything from 100 kilowatt up to 2 megawatt, we normally recommend using the PV system advanced procedure in the system. And if we are exceeding using 200 kilowatt up to 5 megawatt and above, then we recommend using the PV Genset Professional. So again, it's referring to additional sources in the generation in the plant, for example, if we have batteries or we have a hybrid inverter that we need to then subsidize with additional PV, this is where the PV Genset Professional would then come into play. So regarding Fronius support, so to get started, again, we always recommend is to do the Fronius PV Genset checklist, as well as for any planning support we can assist. So with the planning support, we have the checklist for the necessary data. So this will be regarding location, if it is off-grid remote, if it's a backup, sometimes grid-tied, how long does the system operate in the backup situation, hours per day or days per week, and if there's requirements regarding codes, standards, zero feed-in, for example, regarding your country setup. Next is the sizing. So this will be the data sheet. So if it's a single or multiple genset integration that we are doing in the system, as well as the generator's manufacturer or model, as well as any genset controller that is in the system. The normal apparent power of the genset in terms of kVA. So if we had multiples, we then stipulate what the kVA of those generators are in the system, as well as our normal maximum active power of the genset in kilowatts. So we'll need to change from genset A and genset B and C, for example, in the situation back into kilowatts to then desire the maximum active power for the genset. Next is the load data that we need to then enter into the system. So we'll need to say the load profile for 1 year if we have got that data available. If not, then we can then enter the data separately into the graph below. Then the plant PV system size. So again, how much minimum kilowatt peak can we get away with, as well as what's the maximum PV system size that we want to have in the system itself. Then next is regarding your grid operation. So your grid voltage and frequency. So normal grid frequencies, for example, the grid voltages. So your LV or MV, or if it's kV, for example, in the system. And then is also to attach an existing schematic of the existing system. Economics, so again, diesel prices delivered at site, either in euros or in US dollars. The electricity price from the generator itself, so how much we are generating in terms of the power itself from the generator. The real interest rate, if available, as well as the automation period in terms of years, so if it's 5, 10, 15, or 20 years. And this is our Fronius planning support that we offer with regards to doing genset integration into a system. So we always ask for this to be filled out, so it helps give us a basic idea of how we can assist with recommending how to control the system, as well as how to plan and integrate it into it itself. So feasibility, so we help you estimate. So again, with the Fronius system planning support, it allows us to get the optimal PV system size, as well as it allows us to calculate your maximum savings that you can achieve with the system itself, with the PV and genset in the situation. We also get these detailed system analysis. So again, your long-time load profile measurements, your schematic load profile, as well as the genset's detailed analysis itself. Design options, so we can have technical and economic, as well as a detailed report at the end for the system itself. So here we've entered all our details into the report, and here we've calculated a basic annual balance over the optimized PV system size that we can do in the system itself. So here we can see that the proposed size is just at 750 kilowatts, for example. So here we can see with the PV system size, we can have the economic savings as well as the costings, annual costs, as well as your annual savings that we'll then achieve with a system of that size, for example. So Fronius recommends the following controllers into the system. So we recommend DIVE controllers, as well as ELIM, COMAP, and as lastly, in-combi controllers into the system. If you're doing your own generator integration system, we do recommend that you get in touch with the tech support in Austria. They will then be able to assist with having it guaranteed that it will be able to do the control of the system entirely, and they will again give you the green light if it is usable in the system. So the Fronius Inverter solutions. So we have our Fronius Snap Inverter range. So again, this is the Fronius Simo Advanced, which is a 3-phase unit, has 2 MPPT inputs on the inverter, and then power class from 10, obviously up to 20 kilowatts in the system. We then have our Fronius Eco Inverters. Again, it's a 3-phase unit with 1 single MPPT, and this is power class rated from 25 to 27 kilowatts. You can oversize the snap inverters, so it'll differ between the Simo and Eco range, for example, but you can oversize either one of the 2 inverters into the system. Next is Fronius's new unit that we're calling the Fronius Verto. So the application is for small commercial segment systems. So there's maximum flexibility in the DC string design. So we have multiple MPPTs on the new Verto unit that's coming out. It's got also its MC4 connectors on the bottom, for example, on the unit. So allowing for quick disconnects and also monitoring and measuring when doing any work on sites. And this unit will be available in power classes of 25, 27, 30, and 33 kilowatts. You can also oversize these Fronius Verto units, but those details will be released later going into next year when the unit is on the market. Next is the Fronius Taro. So this is Fronius's commercial-based inverter. So we have 2 different variations. So we have the Fronius Taro Eco and the Fronius Taro Standard. So the variants are different between the Taro and the Eco, but both are available as being direct or pre-combined, so allowing us to have MC4 connectors on the bottom of the units for string inputs, as well as doing a pre-combined string design coming into the unit entirely. So the power classes is 50 and 100 kilowatt, but again, this will vary depending on which version you are using. So whether it's Eco, so the Eco is available as both 50 and 100 kilowatt, and the normal Taro is only available in 50 kilowatt variant. With the normal Fronius Taro, you do get 3 MPPTs on the unit, whereas on the Ecos, we only have 1 single MPPT input on the Fronius Taro Ecos. So it's just a bit on the communication interface. So your system data can be transferred in parallel to third-party components and to Fronius Solar Web via Modbus TCP or Modbus RTU. So with the controller example, we're using a DIFE 150 hybrid. So here we're using either Modbus TCP or Modbus RTU to communicate from the controller back through to the inverter itself. From here, we'll then have a LAN connection or WLAN, which will then communicate back to via our router or switch, will then allow us to output our data through to Fronius Solar Web itself. With the use of a snap inverter in the system, it's very the same, except we will have to make sure that we have a data manager 2.0. So this can either be an internal card on the unit or as the data manager box, which is an external card that can be installed. Again, we can use Modbus TCP or RTU to be controlled via the controller itself. So we can use Modbus RTU coming through to the orange block connector, so RS485, to then control the system itself. So we can have a master inverter and then have our slaves in the configuration, just making sure that we have got a data manager card or box to then allow for that communication from the genset controller itself. For any further information, we have got recordings that are available on our homepage. So for operating installation instructions, you can follow the link at Fronius/downloads. And then on our YouTube channel, we've got how-to installation videos, as well as webinar recordings, and a dedicated Sub-Saharan Africa playlist for any additional webinars that you want to view later on. So for any technical questions, trainings, Sales International, as well as after sales service, the details are as following. And our personal details for Sipanokulu, again, who's the TSA for the Western African region, his phone number and email address. Byron Kutzer, myself, I'm the TSA for the Southern African region. Here's my contact details. And then lastly is David Mongi, who is our TSA for the Eastern African region, and his details are as followed below. If you have any further questions, please do let us know, and we will get in touch with you as soon as possible. Thank you for attending today's webinar.
Byron, if you don't mind, I see we have a couple of minutes left. We could see if we can attend to one or two questions that has been asked. So I just want to pop one up here. Probably, if time allows, we could answer two. Let's see. Yes, so Biomi, I think from Nigeria, asks, is asking of what is the maximum loading of the genset? So just a quick answer to that. To be able to ascertain the maximum capacity of the genset, it would entail that you'd have to assess the peak load demand, just like I mentioned in my part of the presentation. Once you're able to ascertain the peak load demand, then you can now estimate what would now be your maximum genset capacity. So just to put it in context, if your peak load demand is 100 kilowatts, then it would do well for you to say, okay, let's go with a genset with 120% higher than the peak load demand, so that you can be sure that the genset would be able to cater or supply for 100% or supply the maximum peak load demand. I hope this is understood. And here Evelyn is asking for a PV genset solution, where is the settings to be carried out to maintain the 30% genset loading? Byron, would you have anything to say about that?
So I'm just trying to find the question here. Which one is it?
Okay, I just randomly selected it, so it's a question asked by Evelyn. It's not numbered, so I wouldn't know. So, but basically, for Evelyn, she's asking
Previous genset
for
solution.
Yeah, where the setting is normally
To
done
maintain.
in order to maintain the 30% genset loading. Have you seen it?
So that is done entirely from the controller itself. That's integrated in the
Exactly.
system. So what you'll do is you'll enter the kVA peak of the genset, and then we'll say 30% of that value is then entered into the controller. And what happens is it makes sure that the genset is covering that X amount of load that's actually referred to by the CTs. And then what happens is after that, then the PV is then allowed to inject the additional power into the system to then compensate once that 30% load has been covered from the genset itself.
Exactly. Great. Thanks a lot. And then finally from Geoffrey. Geoffrey asks, so if the genset is bigger than the PV inverter, and then the load demand drops to below PV power production, would there be any reverse power to the genset? So basically, although I was still attempting to answer this, so basically what happens in this case is that so long as the system is correctly configured, then the PV genset controller would be able to handle this. So what it will do is to automatically drop what the PV is doling into the system, and then if it results to if absolutely necessary, basically the genset takes up control of such situation. I think it hands over the entire capacity of the load, providing for the load to the genset. And having said so, I would also want to add here that in the case whereby there is a glitch in communication, the communication line between the genset controller and the PV, the genset controller automatically shuts off the PV and then hands over the entire power generation to the genset. This is, of course, to forestall any occasion of reverse power or negative feedback, because the sole aim of this particular solution is not only to save fuel, but also to provide maximum protection to the genset.
Yeah.
So
there is other
yeah,
precautions that you can add to the system. So some manufacturers do recommend additional smart meter or to meter that's installed separately. So this will be installed on the load branches with the entire system, not just the genset itself. So it helps to monitor the loads. For example, if they rapidly switch off, then the PV can react quick enough to ensure that no power is then fed back into the generator. It's a secondary precaution in case you have a site where there's high switching off and switching on of big loads, for example, in the system.
Exactly. Thanks, Byron. Great. Thanks a lot for your questions. This was indeed an interesting one. We could tell from all the questions we've been being asked on the chat platform. So thanks a lot for finding time to attend. And until we come your way next time, please do enjoy the rest of the day. So from me, Byron, and the rest of the team, we want to say thanks again for coming and goodbye.